First of all, I'd like to thank the organizers for this wonderful conference, and it's great to see people still here. And I thank the organizing committee for setting up a wonderful program. Okay, so let me set the stage a little. There are two approaches one learns to closure of Cartesian one category. You learn object-wise. You assume that every object, crossing with any object, has a right adjoint, or with every object. And the alternative approach is to specify a bifunctor with the property that C of x, morphism from C cross x to y are bijective, naturally bijective correspondence with morphisms from x to this yz, which is the function space. And in 2020, we showed that y is lax exponential. I'll say more about what this is. An object, the first, that's generalizing the first definition, if and only if it's exponential in D0, and that was for categories that I called gluing categories. So they have something like the Artin-Ray gluing construction. And the examples included small categories, double categories are posets, a double category whose objects are locales, and a double category whose objects are topological spaces. And in fact, so that was every object. And in fact, in the case of CAF and posets, the exponentiability corresponded to exponentiability in D0. So for CAF and posets, every object is exponentiable. So those are objects where what I call lax Cartesian closed. That's not the case for locales and spaces. Anyway, we'll see that these two approaches. So if you go, whoops. I'm standing here because I want the little hand. The bifunctor approach is different from the object-wise approach. So in that original paper, I was interested in the object-wise approach. I was interested in the object-wise approach initially, and I hadn't considered the bifunctor approach yet. Okay. Anyway, so this is the outline. I'm going to hopefully quickly say something about double categories and some of the examples I'm interested in, and then lax double functors and adjoints, and then lax Cartesian closed double categories, and then I'll talk about the object-wise definition a little bit, and then if I have time, I'll talk about lax locally Cartesian closed, when slices are Cartesian closed. Okay, so why lax? The reason, even though most of the products are pseudo, I'm interested in lax because most of the right adjoints are just lax. In fact, in that first paper, in the 2020 paper, there's a specific example to show that at least in the category of posets, that's the easiest example to give, and it's the same example of CAF, that the right adjoint, the exponential is not lax. Okay. Not lax. Okay. So as we've seen, double category is the double categories I'm interested in are the pseudo internal categories in CAT. So you have a D0, a D1. I have my source and target map, which I'm denoting by T, and the vertical, the composition of cells I'm denoting by a circle with a dot in it. So unraveling that, you get D0 gives you the objects, and for me, the horizontal, which are strict morphisms, and the objects of D1 are what I'm still calling the vertical morphisms, the loose ones, and the morphisms from D1 give you the cells of D. And I'm not putting arrows in the cells here because sometimes they go forward, sometimes back. Okay, some of the examples, at least the initial examples I'll be interested in, are the double category spans, the objects are sets, the horizontal arrows are functions, the vertical arrows are spans, and the cells, a cell between one span and another is key functions such as diagram commutes. And you can also do span D for any category with pullbacks, or post-span D for any category with push-outs. CAT is what I'll call CAT has categories as objects, functors as vertical arrows, pro-functors or the distributors we saw in the last talk as the vertical arrows, and a cell from a U to a V is a natural transformation from U to V with F and F sub S and F sub T substituted in. Okay. And one more example, and that is Q. This is very sensitive.
Maybe you can use the arrows as a laptop.
Yeah, but sometimes. Oh, there it is. Okay. Yeah, I guess that's where I'm fine. Sometimes I push the wrong one. So, QREL is the category of Q-value relations, where Q is a quantile. A Q-value relation is a function from this is a Q-value relation from x of s to x of t is a function U from x of s cross x of t into Q. So the objects of Q-value just sets. The horizontal morphisms are just functions, and the vertical morphisms are Q-value relations. And there's a cell precisely when, why am I still doing that? Or maybe I touched that. I was doing that to have a hand together. There's a cell whenever U is less than or equal to V with S of S and S of T substituted in. Okay. And QREL is isomorphic to 2REL, over the quantile too. Okay, a lax functor from F from D to E consists of a functor, which I'm denoting by F sub 0, goes from D0 to E0, and another functor from F called F1 from D1 to E1, compatible with S and T, and we usually drop the 0 and 1 when the context is obvious. And then you have your constraints for the identity and composition, and they satisfy naturally in coherence conditions. And I'm denoting lax double as the two category of double categories and lax functors. And this is the category I'm going to work in because the right adjoints are just lax. And you can talk about oplax and pseudo-functors with the cells going in the opposite direction and in vertical respectively. Okay. So definition, which you can find in the 2018 thesis by Ella Ferry, where she calls category lax pre-Cartesian, category pre-Cartesian, double category, I'm calling it lax Cartesian. If the pseudo-functors, the diagonal functor and the unique functor to the identity if those two functors have right adjoints, and are usually denoted by product sign and 1. I'm not so interested in 1. And these lax adjoints should exist in the category of lax double categories if you want to talk about lax Cartesian. Okay, and D is called Cartesian if the product and 1 are both pseudo. Okay, and I'm defining, there are a number of ways you could do this, but this is the definition I'm settling on to start with. A lax Cartesian double category is called lax Cartesian closed if there's a bifunctor, which I'm just denoting by brackets, from D out cross D into D with bijections, one on D0, which makes D0 Cartesian closed, and one on D1 that makes D1 Cartesian closed. So rather than read them out, I'll just say it that way. And no, you don't have to assume that, you get for free that the product is compatible with S&T by the definition of lax Cartesian. And you're getting that the right adjoint is compatible with S&T because it's a lax functor. Okay. And you can prove that D is not just Cartesian, but lacks Cartesian. Actually, all you need is that the product is up-lax. What did I say? Not only lacks Cartesian, but Cartesian, so you also have the product being up-lax. That D is lax Cartesian closed if and only if D0 and D1 are Cartesian closed and the Cartesian closure structure is compatible with S and T. So I will often in D0 write the right adjoint as exponentials instead of brackets. Okay. And the proof is the forward direction is clear from the definition. Going backwards, we show that the brackets is lax just using the fact that the product is up lax and you're just using the unit of the adjunction in D1.
Sorry.
Yes?
Can you please tell me what is y and z in the theorem?
Yes. In my notation, when I write, let me see if I have one here, let me show you a little picture right there. When I have a u that's going between x's, or well, between y's, okay? I'm just calling, I could have put one on the u and v on there, but I was being, I could say lazy, but really trying to be economical to get as much on as possible. Good, thanks. Okay, for span, so I'm not going to show you any details on this, but I'm just saying what things are. So span is lax Cartesian closed. It's the usual exponential on sets. And for VW, so given, so here you can, that's the trackpad that's making the switch. So if you have a V on the Y's and a W on the Z's, and you want to define the domain that we can't touch, you can't use the little hand. And you want to define the domain of the exponential, you just take this, the set of commutative diagrams, or the set of arrows from, or a set of cells from V to W. And you can show, and I do think I have at least the bare ones of it, and that's the exponential because any diagram of the form, the one on the left, there we go, corresponds naturally if you put in the exponential transpose to one on the right, and you can see that fixing an x, you get the f hat, you get an f hat into this set of diagrams. Okay, and you can also show that this holds for span D, where D is a Cartesian closed category, and you just need equalizers. You can use equalizers to define this, have the set live in your D instead of in sets. Okay. Okay, cospans, the category of cospans is not Cartesian closed. You can show that the source of the thing that's supposed to be the target of the cospan for the exponential isn't equal to the corresponding set of functions from y sub s to z sub s. And the way you can show it, cospan is equivalent to to a presheaf topos. It's just presheaves on the little cospan dots there. Just cospan where each element has each node has one object, and then you can just show using things in what's going on in presheaves. You can just show that the source of the thing that has to be VW in the topos is determined by not just a single thing up here. So when you project down to y to the z to the y, you're not just getting a single thing up here, you're also carrying along a function here. So that can be worked out. So that's not lax Cartesian closed, but you can see that object-wise is, and I'll bring that up again later if I have time. It's when your y's is just a constant, y is just, y is in the of S and a y sub t. Okay, and you can also show that cat is Cartesian closed, and before I used the fact that cat 1 is equivalent to categories over the little category 2, but you can show it directly, and I'm interested in showing it directly for other reasons, which won't be apparent here, having to do with generalizing to real close, but that's another story. Anyway, for cat, folks, so if you have a profunctor, see if I can point without changing. If you have a profunctor V and a profunctor W, and you have, so that has to act on, in that, what my terminology, I'm going from y sub s so I'm going from, so my V is going from y sub s up into y sub t, so I have a sigma there, sorry, a little, I need it, okay, so I need to say what's going on when I, right, so I want to go from z to the s, z to the s to the y to the s, into z to the t to the y to y sub t to the z to the t to the y to the t. So I have a sigma sub s and a sigma sub t. I should put one on the slide. I have a sigma sub s and a sigma sub t, and I take the set of natural transformations from V to W with sigma sub s and sigma sub t substituted in, and you can show that this works. Okay. So here's another example that I haven't been considering before, and that was before with the object-wise stuff, and that's QREL. And you can show that QREL is a lax Cartesian closed category when Q is a locale. And there, the product is just defined. So if you have a y sub s and a y sub t, and a y sub x sub s and a y sub x, and an x sub t and a y sub t, you just take the meat in the locale of u of x sub s, x sub t, and v of y sub s and y sub t. So that's the product. And since you're just on sets, yz0 is just z to the y, and you define the vw. So if you have a v that's going from y sub s cross y sub t into q, and w is the same thing with the t's, you define v comma w of a function, sigma sub s, comma function, sigma sub t. You just take the meat of, and you look at the meat over y sub s, y sub t, of v of y sub s, y sub t, implies, and that's the implies in the locale, w of sigma sub s of y sub s, sigma sub t of y sub t. And you can show that the diagrams from u cross v to w correspond bijectively with diagrams from u to vw, and I did put the sub 1 on there, which I could have dropped. But in any case, you can show that u cross v is less than or equal to w with f sub t, f sub s, f sub t substituted in, if and only if you have u, so I'm suppressing the x sub s, x sub t, is less than or equal to the v of y sub s, y sub t implies w of f sub s with blank y sub s, and same with t's, for all y sub s, y sub t. That's just unraveling the left-hand side, but suppressing the x sub s, x sub t, and that shows you that that's equivalent to u being less than or equal to that v w brackets with f sub s hat, the exponential transpose, f sub t hat. Okay. So that's, I know it's kind of fast, but that's the calculations, just follow your nose. Okay, so that's the examples, or a few examples. There are some more, but that's a few examples to demonstrate that. So now, the double category is, I'm calling object-wise, and this was in the 2020 paper, lax Cartesian closed, if So now I'm not assuming the category is even lacks Cartesian, but I'm assuming that crossing with y exists and has a right adjoint and lacks double for all y. Okay, so we know from the first part that cat, span D, and Q rel, where D and Q are, as I mentioned before, are examples because lacks Cartesian close implies objects-wise lacks Cartesian close. But cospan D actually is. So here's what you see. For D, that's a Cartesian closed category with push-out. So not just sets. A Cartesian closed category with push-outs. Yeah, you don't need the equalizers to form anything. So if you have a diagram like the one on the left, so notice the y's are all the same. So as soon as you don't have the y sub s, whoa, went far. As soon as you don't have the y sub s and the y sub t, you can transpose that into a diagram on the right by just transposing all the y's. And so you can take for your exponential the w to the w to the y to just be taking it pointwise, and that works. Okay. Okay, finally, I think I have time to do this. There's a little typo on this. I apologize, it's at the very end. D is called lacks locally Cartesian. So locally Cartesian closed is just, in the one category, a case is just every slice is Cartesian closed. So here I'm going to say D is lacks locally Cartesian closed if every double slice is lacks Cartesian closed. And I'll remind you, the double slice D over B has as its zero, D0 over B, and as its 1, D0 over the identity on B. So some examples. Cat is not lacks Cartesian closed. Well, we know cat 0 isn't lacks Cartesian closed, but here's a little example that shows you even if cat, the double slice of cat over 2, the 0 part of it, so cat over 2 is Cartesian closed, but its one slice is cat over 2 cross 2. And that is not Cartesian closed. It doesn't satisfy the factorization problem. In fact, almost every D you put into, the same thing happens. In fact, every D but one. Okay, span D is locally Cartesian closed if D has push-outs and is locally Cartesian closed itself, because you can show, just with diagram chase, that span D, the double slice, is equivalent to span of the double slice, D over B. So that's something you can unravel and show. And finally, here's where the typo is. You can show that QRel is lacks locally Cartesian closed if Q is a locale, because you can show in this QRel should be the slice over B. It's pardon me for leaving that out. But you can show that if you take the B upper star Q, which is the internal locale associated with Q in the topos sets over B, and you can show that QRel, the double slice over B, is equivalent to B upper star Q rel of sets over B. So you can show that those are equivalent, and because the computation for QRel is constructive, you just automatically get that this is lacks Cartesian closed. And that's locally Cartesian closed, and that's the end. Here's a few references of things I think there. I wanted to say actually one thing. This all appears in a paper that will be in the TAC volume in memory of Martha Bunga. I'm not sure when that's coming.
This year, I hope.
This year.
So thank you very much for your interesting talk. Are there questions or comments? David?
So do you have some ideas on, like internalizing the concept of Cartesian closed objects, or let's say you have involutive monoidal two category, or maybe some other notion, and then you would like to have this, you can define pseudomonoids, but how about closed pseudomonoids, or maybe monoidal closed objects?
So you're saying just the objects individually, dealing with the, I'm not sure what you're saying. So object, just individually object, not the whole. The whole thing.
Yes, so you have the bigger setting, you're inside of this two category, and then you would say, okay, I would like to have an object that is Cartesian closed in that setting. Like,
no, I haven't thought about, I don't think I've thought about it. I've probably thought about most things about exponentiability, because that goes, I've been thinking about exponentiability for many, many years. But if I understand what you're saying, I haven't thought about it that way.
So you briefly mentioned local Cartesian closure and where it breaks down. You can repair that by changing your notion of slice category. You probably remember this from discussions we had a long time ago. When I was thinking about that, I was trying to work out in domain theory what relative exponential or dependent type exponential exists. I found a way of reducing it to a case that looks like a gluing construction. I don't know whether that's what was in your paper about that subject.
With other slices, meaning what you're putting...
More complicated dependent
The
types.
triangles don't commute on the nose, they commute up to something else. Is that what you're saying? I don't know what other slices you're interested in.
Let's talk afterwards.
Yeah.
Right.
I don't remember talking about it.
Is there any short question or remaining?
You've been talking about the Cartesian closed double categories. Are you also interested in the monoidal
I am,
case?
and I thought about pushing through what of this can be, and I have had some discussions with Christina.
Yeah.
So we're going to try to put some stuff together, but she's, as you know, she's thought about some of this stuff, and she's got some different examples she's interested in. But yes. So a lot of this does go through. Yeah.
Yes.
I was just wondering if there is a notion of internal language for a Cartesian closed double category, like simplified calculus or
So like generalizing what you do for a topos.
something like that.
Yeah. With no other structure besides the Cartesian closed. I mean, you need, so you're saying what you can do when you don't have the other structure.
No,
Yeah.
just more simply thinking like the internal language of a Cartesian closed category normally is the simplified calculus. So I'm wondering whether there is
Oh, for a locally Cartesian closed, you're saying?
for a double category.
Yeah, oh, I don't know, but that might be an interesting question, you know, because you have two Cartesian closed categories, so it may just have to do with certain things in the internal language. You can state in different, you have to state in different places, but that's a good question. Yes.
So let's the speaker.